When a body orbits the Earth at a speed whose centrifugal force counterbalances the Earth's gravity, this is called the first cosmic speed. We have called the speed at which it takes a body just to be able to run a central body the orbital velocity. It's one and the same thing. Therefore, the first cosmic velocity of Earth is generally equal to the orbital velocity of a body around a central body. As we know that the centrifugal force of a rotating body is one of the components of the inertial force. And we also know that a moving body is able to resist all forces acting on it with its inertial force, regardless of the direction of movement. That is, not only when it orbits the Earth, but also when it flies radially outward. Basically, it is quite clear that as long as a body is running at the orbital, first cosmic, velocity, it is totally free from Earth's gravity. It can move anywhere under this gravitational field. And he is already able to leave the Earth. If he wants to walk around the Earth forever, he has to do it in a tangential direction. If he wants to leave the Earth, he is forced to fly outwards. It's certainly not the best method if, for example, you're going east to reach the destination in the north. So it is also possible for a body to leave the Earth at a first cosmic velocity without needing a second cosmic velocity. If a body orbits at a speed greater than the orbital velocity, it will move radially outward. In order for a body to be able to escape from its central body, it needs a certain higher speed, the so-called escape velocity, second cosmic velocity for Earth. The previous second cosmic velocity, as we know, is This equation is derived from the principle that the kinetic energy equals the potential energy of the body. We have already explained in the video how does the pendulum movement work physically, real physics, number 5, that the potential energy cannot be converted one-to-one to kinetic energy, taking into account inertia. Therefore, the suspicion arises as to the correctness of this second cosmic velocity. In the video Double Orbital Velocity Difference Effect, Real Physics, number 16, we explained that if a body orbits at a speed that is in excess v greater than its orbital velocity, it will move radially outward. And its speed will be reduced by twice the orbital velocity difference between radial distance traveled. This effect can be used to test how far a body running around the Earth can move outwards with the second cosmic velocity. Assuming the radial distance between points E and A is r, the orbital velocity difference between them is as follows. If a rocket is launched tangentially at point E with a velocity ve1 delta v greater than the orbital velocity, its velocity at point A is reduced by 2 times delta v. That is exactly the orbital velocity at point A. Consider point E as 1 on the Earth's surface, and VE as the second cosmic velocity. This results in the length of this line. At this point the body is running exactly at the orbital velocity. This is a state of centrifugal equal gravity. However, with the radial inertial force created by radial motion, the body can still travel an equal distance outward, to point B. So with the second cosmic velocity of 11.2 km per second, a body can move a maximum of 2.46 10 to the power of 7 meter outwards. There is no longer any question of leaving the Earth. This calculation is due to the fact that the body always flies exactly in the tangential direction. At point B, the inertial force that propelled the rocket from point A to B is completely exhausted. The missile's outward movement is also stopped. And the rocket's speed is now 1 delta v less than its orbital velocity at that point, and its centrifugal force is also less than Earth's gravity. And it is withdrawn from the Earth and finally reaches the point E again. This is how an orbit was created, just like we told in the video Physical Interpretation for the Origin of the Moon's Orbit, Real Physics, number 17. But at what speed can a body actually escape Earth's gravity when flying in a tangential direction? From the double orbital velocity difference effect, we derived the equation for calculating lunar velocity. This describes that the orbital speed of a body is equal to twice the orbital velocity minus its basic velocity. This equation applies to all bodies running around a central body. From this we see that if an orbiting body does not come back, the radius r0 of the base circle of its orbit must be infinitely large. Then the speed of the rocket at the start on Earth, if it will not come back, is as follows. The radius r0 is equal to the radius of the Moon at point 1 and corresponds to the radius of point A in this example. Also, this double orbital velocity will always decrease by double orbital velocity difference. When a rocket with the double orbital velocity reaches point A, its speed will be as follows. This is also the double orbital velocity at point A. So when a body orbits at twice the orbital velocity, its orbital speed always decreases by the double orbital velocity difference between the distance traveled, but always remains its instantaneous double orbital velocity, up to infinity. As said, even with a simple orbital velocity, first cosmic velocity, a body can escape the gravity of the Earth, if it simply flies radially outwards. When a body moves radially outwards, gravity decreases. As the speed remains the same, there is an excess speed delta v compared to the current orbital velocity. However, this excess is slowed down by the gravitational field. Because, as I said, the strength of the inertia is always the same as that of the attacking external force, i.e. the excess is not guaranteed by inertia, and is defenseless at the mercy of the gravitational field and slowed down by it. So the real speed of a body moving outwards with the first cosmic velocity keeps decreasing, but it always remains the same as the momentary orbital velocity and can therefore fly further and further outwards to the infinitely distant point at which the speed of the body also drops to zero is reduced, theoretically. That is, the escape velocity should be twice the orbital velocity in the tangential direction, or just a single orbital velocity in the radial direction. Thank you very much for your attention. See you next time.